everyone, thank you so much for joining me for this video. Today we're going to be looking at the properties of period 3 elements and their oxides. So we're going to look at the reactions of sodium and magnesium with water, the trends in the reactions of the elements of period 3 limited to the formation of sodium oxide, magnesium oxide, aluminium oxide, silicon oxide, phosphorus oxide, sulfur oxide and sulfur trioxide. We're going to look at the trend in the melting point of the highest oxides of the elements and the reactions of the oxides of the elements with water and the pH of the solutions formed. We're then going to look at the structures of the acids and the anions formed when phosphorus oxide, sulfur oxide and sulfur trioxide react with water. So by the end we should be able to explain the trend in the melting point of the oxides of the elements sodium to sulfur in terms of their structure and bonding, to explain the trends in the reactions of the oxides with water in terms of the type of bonding present in each oxide, and write equations for the reactions that occur between the oxides of the elements sodium to sulfur and given acids and bases. So now we're going to look at the reactions of period 3 elements. We're first going to look at their reactions with water. So only sodium and magnesium react with cold water and also chlorine. So firstly we're going to look at sodium, and sodium has a vigorous reaction with water. And so the sodium solid floats on the surface and fizzes, and it melts due to the exothermic reaction because heat is given off. So it floats on the surface and it fizzes, and then it melts. So we have this equation of sodium reacting with water to form sodium hydroxide and water. And this is a very strongly alkaline solution which is formed because the sodium hydroxide dissociates into Na plus and OH minus ions. And these OH minus ions means that the solution is alkaline. And sodium hydroxide is such a strong base that this reversible reaction is basically a one-way forward reaction. And then number 2 is magnesium. And magnesium reacts very slowly with water at room temperature. And so we have this equation of magnesium reacting with water to form magnesium hydroxide, which is the milk of magnesia. And this is sparingly soluble, so it is a slightly alkaline solution because it doesn't dissociate completely like the sodium hydroxide does. So it's more of an equilibrium that's set up, and also hydrogen gas, which you should see bubbles. And magnesium reacts a lot faster when it's heated and you use steam instead of water. And so you get magnesium added with water to form magnesium oxide and hydrogen. And there shouldn't be any brackets there, it should just be magnesium oxide. Next, we're going to look at period 3 elements and their reactions with oxygen. And all these reactions are exothermic and we form the metal oxides. So first one we look at is sodium, and sodium burns brightly with a yellow flame. And this is the reaction that we have. So we have sodium reacting with half a molecule of oxygen, and it forms a white oxide. So actually with all of these reactions, a white oxide is always formed. And then for magnesium, magnesium burns with a white flame, and it gets more intense after lowering it into a gas jar. So it burns with a white flame and it gets more intense after lowering it into a glass jar. And here's the equation that we have. So we have magnesium reacting with oxygen to form a white oxide, magnesium oxide. And then for aluminium, it burns brightly with a white flame again, like magnesium, and it forms a white oxide again. And aluminium is actually really reactive, but it's always coated with a layer of oxide, and this protects it from further reaction. And then for silicon, silicon reacts with oxygen to form silicon oxide, which is again white. So for all of these period 3 elements, you need to remember all of these equations, and also what colour flames they have, and what's formed when they react. So for phosphorus, there are 2 types of phosphorus. There's red phosphorus and white phosphorus that you need to know about. Red phosphorus needs to be heated before it can react, but white phosphorus just ignites as it is in air, and a white smoke, which is the phosphorus oxide, is given off. And P2O3 is produced if there is not enough oxygen. For sulfur, sulfur needs to be heated before it can react with oxygen, and it burns with a distinct blue flame. It also produces sulfur dioxide, which we class as a choking gas. Next, we're going to look at the trends in melting points of period 3 metal oxides. So the metal oxides are formed when we react to the period 3 metals with oxygen. And so here is the graph of the melting points. So sodium oxide, magnesium oxide, and aluminium oxide all have very high melting points. And this is because they are all giant ionic structures, because it's a metal and a non-metal bonding together. And so they have many strong electrostatic forces of attraction between the oppositely charged ions, and these extend throughout the whole structure. And so these kinds of forces take a lot of energy to break, and so their melting points are really, really high. So things you need to remember are that they are giant ionic, so there are lots of strong electrostatic forces of attraction between the oppositely charged ions, and they extend throughout the whole structure, so they take a lot of energy to break. And then coming to silicon oxide. Silicon oxide has a giant covalent structure, so it has lots and lots of strong covalent bonds that take a lot of energy to overcome, and that's why its melting point is not too much lower than the ones for the giant ionic structures. And then for phosphorus oxide, sulfur trioxide, and sulfur dioxide, these all have simple molecular structures. And so what we know about simple molecular structures is that they only have weak van der Waals forces between the molecules. And these don't take very much energy to overcome. And so they have much lower melting points compared to the giant structures of the giant ionic and the giant covalent. Now, the reason that magnesium oxide has a higher melting point than sodium oxide is because the charge density of the Mg2 plus ion is higher. Because for magnesium, it forms Mg2 plus ions, but for sodium, it only forms Na plus ions. That means that the magnesium 2 plus ions bond with the O2 minus ions more closely, and there's a stronger attraction between them. And so this leads to stronger electrostatic attraction, and so more energy is needed to overcome these forces of attraction. So the melting point of magnesium oxide is a lot higher than for sodium oxide. And then aluminium oxide is predominantly ionic, but it actually has some covalent character. And this is due to the Al3 plus ion being quite small. So it can get really close to the O2 minus ion, and it distorts the electron cloud of this O2 minus ion. And so the ions aren't perfectly spherical anymore. And this means that there's some covalent character, and so the melting point is slightly lower than for magnesium oxide. And also for all the simple molecular structures, how we know which one has the higher melting point is by the size of them. Because phosphorus oxide is a bigger molecule, it has more electrons, and therefore it has stronger van der Waals forces between the molecules. And so that means that it takes more energy to overcome these stronger van der Waals forces. And so it has a slightly higher melting point than sulfur trioxide and sulfur dioxide, which are slightly smaller molecules. So we're now going to look at the reactions of period 3 oxides with water. So the first one we're going to look at is sodium oxide, and sodium oxide dissolves and reacts with water to form sodium plus ions and hydroxide ions. And so it has a very, very alkaline solution. Well, it forms a very alkaline solution with a pH of around 14. Now, what you need to know about these reactions is that you need to know the equations, and you also need to know the pHs of the solutions formed. So the next one we move on to is magnesium oxide. And magnesium oxide is slightly soluble, so it'll still react with the water, and it will form the magnesium hydroxide again, which is the milk of magnesia for indigestion medicines. And this magnesium hydroxide, because it's sparingly soluble, it forms equilibrium with Mg2 plus ions and also hydroxide ions. And so it forms a slightly alkaline solution. So not as strong as for the one that we saw before, but this has a pH of around 9. Then for aluminium oxide and silicon oxide, they are both insoluble. For aluminium oxide, this is because of a very high lattice enthalpy. So lots of energy is needed to separate the ions of the solid ionic lattice. And then for silicon oxide, it's insoluble because of the very, very strong covalent bonds that it has, which take a lot of energy to overcome. And then we have phosphorus oxide, and phosphorus oxide reacting with water is actually a very, very violent reaction, and it forms this phosphoric acid, and so it forms an acidic solution with a pH of around 2, so quite strong, but not very, very strong. And this phosphoric acid dissociates to form the H plus and the H2 PO4 minus ion, and it's because of this H plus that we get an acidic solution. Because if you can remember from acids and bases, how we work out the pH is that the pH is equal to minus log to the base 10 of this concentration of H plus ions. So if this concentration of H plus ions is very, very big, then the pH will be very, very small. And so this is why we have a pH of around 2, because it's an equilibrium and it's not just a straightforward reaction like a one-way. And then we have sulfur dioxide, and this also dissolves and reacts with water, and it forms sulfuric 4 acid with a pH of slightly higher, so it's slightly less acidic. And this is because also an equilibrium is set up where they have H plus ions going into solution and HSO3 minus ions. So again, the H plus is what provides the acidity. And then sulfur trioxide is a very violent reaction. And this is the equation we have. So we have sulfur trioxide reacting with water, and this forms sulfuric acid. And this is an extremely acidic solution. It's the most acidic, and the pH is around 1. So we can actually get 0, but a pH of 1 is very, very low. So it's very acidic. And this is because sulfuric acid is a very strong acid. So it fully dissociates. So it becomes 100% ionized in water. And because we have lots of these H pluses being formed, that means that the solution is very acidic. So the general rule to remember is that metal oxides dissolve to form alkaline solutions, and non-metal oxides dissolve to form acidic solutions. And so we have metal oxides dissolving to form alkaline solutions, and then we have non-metal oxides dissolving to form acidic solutions. So it's really important to remember what forms alkaline and what forms acidic, and also their relative pHs. And now we're going to look at the reactions of these period 3 oxides with acids and bases. So sodium oxide and magnesium oxide both react with acids to form a salt and water. So we have sodium oxide basically acting as a base, and then sulfuric acid, which is acting as an acid. And so this forms salt and water. Aluminium oxide reacts with both acids and bases, and we call this kind of behavior amphoteric. So when it reacts with an acid, it reacts, for example, with hydrochloric acid to form AlCl3, so aluminium chloride, and water. And when it reacts with a base, it reacts with hot and concentrated sodium hydroxide and water to form sodium aluminate. And it's really important to remember these two products in particular, because you'll definitely be asked about that. So you'll be asked what happens when aluminium oxide reacts with acid, and also what happens when it reacts with a base. So it's really important to remember the equations, and also the different products that are formed depending on whether it reacts with an acid or with a base. And quite a useful thing that you can use to sort of remember the difference is that this one, where you've reacted the aluminium oxide with a base, it has this OH minus, so you kind of feel like it's been added with a base compared to AlCl3. So if you want to try and remember which one's which, then that could help you. And then silicon dioxide and sulfur dioxide both react with bases. So silicon dioxide is acting as a weak acid, and so we react it with hot and concentrated sodium hydroxide, which is the base, and we form sodium silicate and water. And then sulfur dioxide reacts with the sodium hydroxide to form sodium hydrogen sulfate. And then this sodium hydrogen sulfate can also react again with sodium hydroxide to form this sodium silicate and water, like for silicon dioxide. And then the last one is phosphorus oxide, and it reacts with an alkali. And really, how we think about this is the reaction of phosphoric acid with an alkali, because this is what's formed when phosphorus oxide reacts with water. So here, the H3PO4 is this phosphoric acid. And that's what you get when you basically dissolve phosphorus oxide, which is P5O10. And so the first thing that happens is that because H3PO4 has 3 of these hydrogens, that means we lose 1 hydrogen each time. So we've lost a H plus in the first reaction, and then in the second reaction we've lost the second H plus, and then the third reaction we've lost the third H plus. And so the overall equation turns out to be H3PO4 aqueous plus 3 of these sodium hydroxides, and this forms Na3PO4 and 3 waters. So if they ask for the overall equation, then remember that we need to add 3 sodium hydroxides, because the phosphoric acid has 3 H pluses that I can give away to the base. And what's important for the exam is just to remember all of these equations. Now we're going to look at some questions. So for question 1, the table below contains data that shows a trend in the melting points of some oxides of the period 3 elements. For A, explain in terms of structure and bonding why sodium oxide has a high melting point. Well, if we have a look at sodium oxide, it's made up of sodium ions and oxide ions. And so it must be ionically bonded. And ionically bonded compounds only exist as giant ionic. So it's a giant ionic structure or lattice. And so it has strong electrostatic forces of attraction between oppositely charged ions. And that means that it takes a lot of energy to overcome these forces, and so it has a very high melting point. And then for B, use data from the table above to predict a value for the melting point of sulfur oxide. Now, sulfur oxide that is made up of 2 nonmetals, so it's either simple molecular or giant covalent. And it actually forms a simple molecular structure, so the melting point will be quite low. So we could guess the melting point to be maybe 100 Kelvin, just something a lot lower than everything else in the table. And then for C, suggest in terms of structure and bonding why the melting point of sulfur oxide is different from that of phosphorus oxide. And this is because the sulfur 4 oxide, another name for it is sulfur dioxide, so it's SO2, and the phosphorus 5 oxide is actually P5O10. And so this molecule is much bigger. And so even though they are both simple molecular structures, because the molecule of phosphorus oxide is so much bigger, it has more electrons, and so there are stronger van der Waals forces between the molecules. And so this takes more energy to overcome, and so the melting point of phosphorus oxide is a lot larger. And we have that this is a larger molecule, more electrons, and stronger van der Waals forces. And then for D, write an equation for the reaction of sulfur oxide with water. And now we have to think about what happens when we react period 3 oxides with water. And so what we need to first remember is that non-metal oxides will produce an acidic solution. And so this sulfur oxide or sulfur dioxide will produce an acid. And then for D, write an equation for the reaction of sulfur 4 oxide with water. And the first thing we need to remember is what happens when we dissolve a non-metal oxide, a non-metal period 3 oxide. And what happens is that an acidic solution is formed. And so we have SO2 reacting with water, and this forms H2SO3. And then this can form H plus ions. So in an equilibrium, we get H plus ions and SO3 2 minus ions. And so this helps us with E, suggest the pH value of the resulting solution. It's actually around 1, because this equilibrium here is actually very close to just a forward reaction, because H2SO3 is quite a good Bronsted-Lowry acid. And so lots of the H pluses are formed, and so the pH is quite low. And then for F, silicon 4 oxide is insoluble in water. Explain using an equation why silicon oxide is classified as an acidic oxide. Now, it's an acidic oxide because we can react bases with it and neutralization occurs. And so the equation we have is that we have silicon oxide and we add it with a base such as sodium hydroxide, and this forms sodium silicate and water. And so it's neutralized the alkali, and this is why we call it an acidic oxide. Before I move on to question 2, feel free to click off the video and try it for yourself first. So for A, state the type of bonding in magnesium oxide and outline a simple experiment to demonstrate that magnesium oxide has this type of bonding. And so magnesium oxide is made up of Mg2 plus ions and O2 minus ions because it's a metal and a non-metal. And so this leads us to think that it's a giant ionic lattice. And so ionic bonding is present. And one way that we can demonstrate this is if we use the knowledge that things that are ionically bonded only conduct electricity when they're melted. And so the simple experiment that we can do is just to melt it, and if it is ionically bonded, it will conduct electricity, because then we'll have free ions which can carry the charge, compared to when it's solid, it doesn't conduct electricity because all the ions are fixed. And so when solid, it will not conduct electricity. And then for B, state the structure of and bonding in silicon dioxide. Other than the high melting point, give two physical properties of silicon dioxide that are characteristic of its structure and bonding. And so the structure is that we've got silicon reacting with oxygen to form silicon dioxide, and so it must be covalent. It must be covalently bonded because it's two nonmetals. And silicon dioxide is actually one of the examples that you need to remember. So it's a giant macromolecular structure. So that's just another name for giant covalent. And give two physical properties. One is that it'll be insoluble because of those strong covalent bonds that take a lot of energy to overcome. And also, a very obvious one is that it doesn't conduct electricity. And this is because there are no delocalized ions or electrons to carry any sort of charge.